In this example, we're being asked to solve a system of linear equations, in other words, find the value of the variables x, y, and z. And what we'll do to solve this problem is we'll put it into matrix form and then use basic row operations. So let's first of all check to see that we've got a matrix where the coefficients actually fit. So we can see here we've matched the colours of each equation with each line of the matrix. It'd be wise to pause here and think about what row operations you would use to reduce this down to a form where it's easy to solve for the variables x, y, and z. Given our aim is to reduce the bottom left-hand corner of the matrix to zeros, what we might want to do is first of all look at row 2. And we see here we've got colours for the first entries of row 2 and row 1, in other words blue and red. And what we'll do to reduce the first entry of row 2 to 0 is go 2 minus 2 lots of 1. In other words, row 2 minus 2 lots of row 1, and we've put that instruction on the right hand side of the matrix. And likewise for row 3, to make that first entry a 0, what we'll do is we'll go 3 minus 3 lots of 1, or expressing that in row operations, row 3 minus 3 lots of row 1. It would be a good idea to pause here, perform the row operations, and see if you agree with the final result. So what you should get is a matrix that looks like this. We've got zeros in the last row, and in the second row we've got all zeros with a 3. Now if there are zeros in the last row, does that mean that there's infinite solutions? Well, normally yes, but we do have to investigate further, and the second row tells a different story. So the second row actually has the equation 0x plus 0y plus 0z equals 3. In other words, 0 equals 3. Now this isn't valid. So despite the last row, the second row indicates to us that there's no solutions. So let's consider again what the last row of the matrix tells us after we perform the row operations. If we see a case where there's all zeros with a constant at the end not equal to 0, that means that we've got no solutions. It's basically like saying 0 is equal to a non-zero number. If in the second case we've got zeros along the last row, that basically means that that equation is no longer valid. It's like saying 0 equals 0, so it's not really part of the system anymore. So we have, in the case of 3 equations, more variables than there are equations, so we've got infinite solutions. Or in the last case there, we can see the typical case, which is where we've got a unique solution. But in each one of those cases, what we need to do is bear in mind what we just saw in the last example, and we must investigate what happens in the rows other than the last row when we perform the row operations. Let's now consider what the example might look like when we consider the situation of 3 planes. Now when you've got 2 planes intersecting this line here, we have an infinite number of solutions. If we introduce a third plane, which is parallel to the one below my hand, these 2 planes are such that they never intersect, so that there is no point or no line where the 3 planes intersect. So we see again an infinite number of solutions for those 2 planes, but introducing a third plane parallel to another, we have no solution.